For thermochemical heat storage, we're talking about sorption, so the take-up of vapor in a material and release of vapor from this material. So this is the general idea. We have a composite material, for instance, salt hydrates. If we add heat, we can desorb the vapor and keep the partially dehydrated material. If we let the dehydrated material react later with the vapor, heat is released again. And an example is the salt hydrates taking up vapor to produce the salt hydrates and heat. And the other way around, if we heat the salt hydrates, we can split it again in the original components. So we can use that for heat storage. I want to go into materials now, but just to give you some feeling for what a typical system could look like, I would also like to show you this figure. So assume that we have a seasonal closed sorption heat storage system. And for instance, here we have a vessel with a salt hydrates, like this vessel. During summer, we heat up the material with heat from a solar collector installation, thereby drying the salts, and the water vapor flows out and is condensed over here in this condenser vessel. So then we are charging the material. If we discharge the system, we evaporate water with low temperature heat from a borehole, say 10-degree heat. Flows concentrated salt, reacts with a higher temperature, a usable temperature, and this heat we extract again by heat exchanger, and we can transport it to a water tank. And there we can extract the heat for tap water heating and space heating. A critical issue in this system again is the heat transport. So as you can see, there is a lot of heat exchanger in this tank to be able to extract and get in the heat. Here you also see the heat exchanger area, and here again you see the evaporator. So during summer we heat up, vapor is flown off, it's condensing over here. In winter the water is evaporated with low temperature heat from the ambient, is reacting with the salts, and high temperature heat can be taken off. So we have different types of materials. We can have absorption in solids. These are typically, this is typically chemical, and in absorption in solids, that means that the water is really taken up in the lattice of the solid, such as the salt hydrates. We can have absorption in liquids. If we have, there are a number of liquids, if we have strong concentration of liquids, these are also hygroscopic. And if you add water vapor, a significant temperature effect occurs. So we can cycle these liquids between strong versus diluted solutions of the liquids. So if we have a strong solution, we add water vapor, we get a diluted solution and heat, and vice versa. And finally, we can have adsorption in solids. These are physisorption materials. And in adsorption in solids, then adsorption is a surface effect. So typically what's happening here is that we have materials with a very large internal surface area, so very porous materials. And then the vapor can adhere at the internal surface of our materials. So in absorption materials, it's inside in the lattice structure, and adsorption is at the internal surface. Adsorption is typically a van der Waals effect, van der Waals forces, and absorption is more like chemical bonding. So here we have again an overview of materials. Well, these are just the three classes I mentioned before: absorption liquids, absorption solids, adsorption solids. Well, for liquids, absorption in liquids, we can, for instance, use concentrated solutions of various salts. Lithium chloride, lithium bromide are well-known salts, also calcium chloride. Also, work has been done on concentrated solution of sodium hydroxide and sulfuric acid. In addition, instead of salt solutions, we can also use certain organic solutions. And then also we can dissolve ammonia in water. So now we are not dissolving water vapor in solution, but we are dissolving ammonia in water. If we look at absorption in solids, we can have more weak chemisorption by various vapors in salts, such as water in salt hydrates, or ammonia in salt ammoniates, or methanol in salt methanolates, or ethanol to explain more. So we can have these, but we can also have stronger chemisorption reactions, such as in metal hydride reactions, oxide hydroxide reactions, and oxide carbonate reactions. And well, all these will be explained further later on in this lectures. Then for adsorption, we typically have materials with a large internal porosity, such as zeolites, silica gel, activated carbon, activated aluminum. Activated simply means that it has a large internal porosity. So you have to produce this material in a specific way. Also, we have aluminophosphates, various types, and we have metal organic frameworks. These two are newer materials, also in research phase. Many of these of silica gel, activated carbon, activated alumina, and many types of zeolites have a long history already in practical use. So these are well-known materials. First, let's have a look at salt hydrates. So we are talking now about on absorption in solids. Well, I've shown you this figure before. Here we have calcium chlorides, and here we have calcium chloride 6 hydrates with all the water molecules in crystal lattice. Then here we have the total energy released in kilojoule per mole versus number of water molecules in my material. And I just put some salt hydrates in here. And as you can see, that's fairly nicely a straight line. In addition, I plotted here the line representing the amount of energy required to vaporize the same amount of water. And as you can see, the evaporization energy is a bit less than the reaction enthalpy, but not that much. This means that if I add water vapor to my salt, in the case of 8 molecules of water, this amount of energy would be released. If I would pour liquid water on my salt, then this amount of energy would be released, because I will need this amount of energy to break the bonds between the water molecules in the liquids. So there is a clear reason why in these absorption storage systems you want to work with vapors instead of liquids, because if you work with vapor adhering, you get a much larger energy density than if you would pour a liquid over the solid.